Hello everyone. Today we want to talk about 15.6 tangent planes and linear approximation part 2. In calculus 1, we learned what a linear approximation is. So let's make a quick review. The linear approximation to the function f of x at the point x equals a is given by this function L of x, which is f of a plus f prime of a times x minus a. Before we keep talking about this, let's make a quick review about the tangent line. So if we want to find the tangent line to the function f of x at the point x equals a, then we will use the Poinsot form. So y minus the y value equals the slope, and the slope of the tangent line is f prime of a times x minus a. So you can see that right here, if we add f of a on both sides, then we will have this L of x. So basically, L of x is the y value on the tangent line. So what is the linear approximation? So remember, we use the tangent line to approximate the value on the curve. That is a linear approximation. For example, right here, if I want to evaluate this point right here, okay, so so let's say this is x, and that will be my f of x, which is the real value. But sometimes we won't be able to find this real value easily. For example, if your curve is sine of x and I want to find sine of 2, then without using a calculator, I don't know what the value of sine of 2 is. However, you can see that right here, this value, okay, this value right here is L of x, which is your approximation. And you can see that L of x, this y value L of x, and the y value f of x are very close to each other. So that's why we say at the point near A, and this A is what we call the center. Okay, at the point near A, we will have f of x approximately equal L of x. So in short, we say that the y value on the tangent line is an approximation of the y value on the curve. So the y value on the tangent line is your L of x, and the y value on the curve is your f of x. Okay, so they will be approximately equal to each other. So this is what we learned in calculus 1. Now we just want to extend this idea to calculus 3. So let's take a look at this definition box. So f is your differentiable function at a point a comma b, and the linear approximation to the surface z equals f of x comma y at this specific point is the tangent plane at the point. Okay, so this is really important. It is the tangent plane at the point. Just like previously, your linear approximation is your tangent line at the point. Okay, the tangent line at the point. So right here, we want you to find out the equation of your tangent plane. So notice that previously we have the linear approximation is the y value. Right here, your linear approximation will be your z value. Okay, so we say this is a z value on the tangent plane. Okay, and we learned how to find the tangent plane in our previous lecture note, and we say that there are two different approaches. Okay, and the second approach is a preparation for this lecture. Okay, so let's take a look at this really quickly. So if you take a look at 17-1, and right here you can see that our z, okay, the equation of the tangent plane, our z is f of a comma b plus f sub x a comma b times x minus a plus f sub y of a comma b times y minus b. And we also review, okay, the tangent line in calculus 1, and we do a one-to-one correspondence. So hopefully this will help you to memorize the formula a little bit. So let's go back to our lecture notes. So right here we will have our z value f of a comma b plus our partial derivatives f sub x a comma b and the f sub y a comma b, and then multiply by x minus x value and y minus y value. Okay, y minus y value. So this is the z value on the tangent plane. And just like what we learned in calculus 1, we use the y value on the tangent line to be the approximation of the y value on the curve. So right here, okay, right here, at the points near the center a comma b, we will have f of x comma y approximately equal L of x comma y. So let's write down the similar description right here. So the z value on the tangent plane is an, do we have enough space? Never mind. Approximation of the z value on the surface. Okay, so when you put your prerequisites, okay, along with your current material, you can do a comparison, and you can see that this is a simple extension of what we learned before. Okay, so again, the z value on the tangent plane is an approximation of your z value on the surface. Now let's take a look at example 1. We have our function f of x comma y equals phi over x squared plus y squared, and we would like to find a linear approximation to the function at the point -1, 2, 1. Okay, so to find the linear approximation, we will use the formula right here. Okay, the formula right here. And you will need to have the z value, which we have. That will be 1 right here. But we also need our partial derivatives. Okay, so let's write down the partial derivatives. So f sub x of x comma y. Right here, you can think of f of x comma y as phi times x squared plus y squared to the -1. So when you take the derivative, you just need to apply the power rule. Okay, so we should have a -5 times x squared plus y squared and then square. But don't forget, this is a composite function, so you will need to multiply by 2x because of the chain rule. Okay, and f sub y right here, you will do the same thing. That will be -5 times x squared plus y squared, and then you have to square it and then multiply by 2y. So our f sub x at -1, 2 should be, let's see, what's our denominator? 4 plus 1, 5, 5 squared. So I have a 25, and I have -2 times -5, so that would be a 10. So that would be 2 over 5. And f sub y right here will be 25 in the denominator, of course. And then we have a -5 times 4, so -20. And when you divide both top and bottom by 5, you have -4 over 5. Okay, -4 over 5. So thus your linear approximation will be your z value plus your partial derivatives plus -4 over 5. Okay, your partial derivatives times x minus x value, y minus y value. Okay, so you have 1 plus 2 over 5 times x plus 1. And then minus 4 over 5 times y minus 2. So this will be your linear approximation. Okay, so let's do some practice. We will take a look at learning activity 17-2-A, number 1. Okay, so right here, given that f is a differentiable function with all these values, okay, f of 2 comma 5 equals 6, f sub x of 2 comma 5 equals 1, and f sub y of 2 comma 5 equals negative 1. Now you would like to use a linear approximation to estimate this value. Okay, but first you want to find the linear approximation. And we know that the linear approximation right here should be f of a comma b plus f sub x, a comma b times x minus a, plus f sub y of a comma b times y minus b. Okay, again, this is your tangent plane. Now, of course, our point of interest is 2 comma 5. So basically, we want to put in this information. So L of x comma y should be this value is 6, okay, and then plus your partial derivative of with respect to x will be a 1 times x minus the x value plus your partial with respect to y will be negative 1. Okay, so negative 1 times y minus y value. So basically you have 6 plus x minus 2 minus the parentheses of y minus 5. Okay, now let's go back to the lecture note and we will come back to this problem later. So this is the first part. You want to find a linear approximation. Now, if you scroll down to the second page, you can see that we would like to use this linear approximation to estimate the value of f of negative 1.05, comma 2.1. So we will need this linear approximation. So let me do a copy and paste. So that will be copy and paste. Okay, so we will put this right here. Now remember, this is the z value on the tangent plane. And we say that we want to use the z value on the tangent plane to be the approximation of the z value on the surface. Okay, so let's take a look at this again. The z value on the tangent plane is an approximation of the z value on the surface. So basically, we have f of x comma y approximately equal L of x comma y. So let me put it right here. So this is the whole idea for your linear approximation. You want to approximate something. Okay, you want to approximate something. So our f of negative 1.05, comma 2.1 is approximately equal L of negative 1.05, 2 comma 1. Okay, so notice that right here, the notation I use is approximately equal. Okay, so don't use equal sign right here because they are not the same value. Okay, so take a look at this picture. You can see that right here, this is our this is our true value, but this is our approximation. They are not the same thing. Okay, the y values are not the same. Okay, so when you extend this idea to Calc 3, you will see that the z values are not the same. Okay, so we use this notation, approximately equal. And then we will use equal sign because right here, L of x comma y equals the whole thing right here. So you use the equal sign from here. And we have 1 plus 2 over 5. And our x value is negative 1.05 plus a 1 minus 4 over 5 times our y value, 2.1 minus 2. So you can see that previously we have our linear approximation in this form on purpose. We don't try to simplify it. Okay, because usually the problem will give you some x value near -1 and some y value near 2. Okay, so when we plug in the x and the y right here, we will do some simplification. So if you try to simplify first, then when you plug in some x and y values, it will become more complicated. Okay, so right here we will have 1 plus 2/5 times, we have 1 minus 1.05, so negative 0.01, minus 4/5 times 0.1. Okay, and I believe this should be 1 minus, this should be 0.02. Oh, this is, wait, this is 0.05, right? I make a mistake. So one right here, negative 1.05 plus 1, so 0.05. Okay, so when you do cancellation, that will be negative 0.01 and multiply by 2, negative 0.02. Okay, so that's better. Okay, and then we have minus. If you divide 0.1 by 5, that should be 0.02. And 0.02 multiplied by 4, 0.08. Okay, 0.08. So we have 1 minus 0.02 minus 0.08. So that should be 0.9. So approximately, f of negative 1.05 comma 2.1 is 0.9. Now right here, you don't have to double check this, but I use calculator. Okay, so calculator. Okay, by using a calculator, the exact value for f of negative 1.05 comma 2.1 is 400 over 441, and approximately equal 0.9070. And you can see how close these two values are. So I would say that our 0.9 is a very good approximation. Okay, again, you just want to find approximation. You don't really want to find the true value. Okay, because the z value on the surface and the z value on the tangent line will not be the same. Okay, except for the tangent point, of course. Okay, now let's go back to our previous learning activity problem and finish that. Right here, we have our linear approximation, and we would like to use it to estimate f of 2.2, comma 4.9. Okay, so f of 2.2, comma 4.9 is approximately equal L of 2.2, comma 4.9. And right here, I will just plug in 2.2 for x and 4.9 for y. So I have 6 plus 2.2 minus 2 minus 4.9 minus 5. So that should be a 6 plus 0.2. And then minus negative 0.1. So we should have a 6.3. Okay, 6.3. Okay, let's practice one more. We would like to take a look at exam 2 from spring 2025. And we will take a look at multiple choice question number 2. Okay, multiple choice question number 2. We want to use the linear approximation of your function f of x comma y at the point 2 comma 5 to approximate f of 2.2 comma 4.7. So first, I want you to write down the linear approximation. Okay, so the linear approximation right here should be 6 plus 2 times x minus 2, and then plus 4 times y minus 5. Okay, and then for f of 2.2, 2.2, comma 4.7, you simply plug in, and right here, remember to use this notation, approximately equal. So I will just plug in 2.2 for x and 4.7 for y directly. So we have 6 plus 2 times, this will be a 0.2, and then plus 4 times, this will be a negative 0.3. Okay, so we should have a 6 plus 0.4 minus 1.2. Wow, what's that? That would be 6.4 minus 1.2. So that should be a 5.2. So we will choose C. Okay, so again, I think the major part right here is to know how to write down your linear approximation. And once you have the linear approximation, then you can just plug in the points to find the approximation. Now let's go back to our lecture note. The second topic we want to introduce today is the differential. Okay, to be more specific, we want to introduce the total differential. So first, let's make a quick review for the material in Calc 1. For y equals f of x, we say that the differential of y is dy, which is f prime of x dx. So basically, you can think of this as dy over dx equals f prime of x, and then multiply both sides by dx to get the formula right here. Okay, so multiply both sides by dx. So our total differential right here, by using the similar idea, you have the derivative, okay, times dx. And right here, because z is a function of two variables, so we don't really have the derivative. Okay, we do have partial derivatives. So we have partial z over partial x and partial z over partial y. And then we wanted to multiply by dx and dy respectively. Okay, so right here you can see the correspondence, the derivatives, more specifically the partial derivatives. Okay, and then dx, dy right here. Okay, so just like our tangent line versus tangent plane, okay, our differential versus total differential, you can see that this is a very simple extension. Okay, now let's take a look at example 2. We would like to find a total differential for the function z equals 2x sine y minus 3x squared y squared. So we know the total differential dz. Okay, so maybe let's write down the sentence. The total differential of z is defined to be dz, which is partial z over partial x times dx plus partial z over partial y times dy. So right here, I wanted to find a partial derivative with respect to x, and that should be a 2 sine y minus 6x, 6 times x times y squared. And then you multiply by dx plus the partial derivative with respect to y. So I have 2x cosine y minus 6x squared y, and then multiply by dy. Okay, so you can see that the total differential right here is not too difficult. Okay, once you remember the formula, it's just like very straightforward. So if you want some practice, you can take a look at learning activity 17-2-A, number 3 right here. Okay, you want to find the total differential for this function. Okay, so make sure you practice this on your own. Now let's go back to our lecture note. Why do we want to learn this total differential? Now, in Calculus 1, after we learn the differential, we say that delta y is approximately equal the differential dy. So notice that delta y right here is the change in y. Okay, it's the change in y. Now it will be approximately equal dy. Now notice that if you have a graph like this, and this is your x1 and this is your x2. So that means this will be your y1 and this will be your y2. So the difference right here will be your delta y. Okay, but when you have this tangent line right here, this guy right here is your dy. Okay, because this is dx, dy over dx will be the slope of the tangent line, right? The slope of the tangent line. So this will be your dy, but the whole thing, okay, the whole thing from here all the way to here, that will be your delta y. And you can see that they are not the same, okay, but it's close enough. So we say that delta y is approximately equal dy. And now you just need to extend this idea to Calc 3. And we say that delta z, okay, which is the change in z. We say that delta z is approximately equal the total differential dz. Okay, total differential dz. Okay, now before we practice example 3, let's take a look at learning activity 17-2-B. Okay, 17-2-B, and we will take a look at number 3. The question asks you, near the point 1, -2, 1, is the function most sensitive to changes in x, y, or z? Okay, now you might be wondering what does this problem have to do with total differential? Okay, because it says most sensitive to change in x, y, or z. So that means when you change x, change y, change z, the function will change, right? The function will change. So we know that right here, the real change in f, okay, the real change in f should be approximately equal the total differential df. So that's why we want to find the total differential. Okay, because you don't really want to plug in the real change in x or the real change in y or the real change in z. Okay, so let's do an approximation. And we know that the total differential right here, notice that f is a function of 3 variables. Okay, so you should have 3 terms. So that would be partial f over partial x times dx plus partial f over partial y times dy and plus partial f over partial z times dz. Okay, and right here we will need to evaluate the point later. So let's don't write the equal sign. Okay, instead let's find the partial f over partial x and the other partial derivatives respectively. Okay, so we should have a 3x squared minus 2y plus 2xz. Okay, and partial f over partial y should be negative 2x. Nope, that's just negative 2x. Good. Partial f over partial z should be x squared plus 7. Okay, x squared plus 7. So that means right here, your partial f over partial x at the point 1, -2, 1 should be, we have 3 plus 4, that would be a 7, and then plus 2, that would be a 9. Okay, good. Partial f over partial y at 1, -2, 1. This is more straightforward, -2. Partial f over partial z at 1, -2, 1, and that will be 8. So your total differential, okay, your total differential right here, okay, so I want to keep my work neat, okay, so that's why I draw some lines to separate, okay, to separate the blue and green work apart from my red work. Okay, so your partial with respect to x at the specific point is 9, so I have 9 dx, and then minus 2 dy plus 8 times dz. Okay, so well, I have an idea. How about this? Yeah, that's better. Okay, now you can see that right here, the change in f is approximately equal 9 times dx minus 2 times dy plus 8 times dz. And notice that although dx is not delta x, dy is not delta y, dz is not delta z, they are in fact the changes in x, y, and z. Now, let's go back to our previous lecture note for a while. Right here, you can see that we say that this length is dx, and this is your dy. But you notice that dx happens to be your delta x. So if you try to extend this idea, okay, dz is not the same as delta z, but dx and dy are the same as delta x and delta y. Okay, so maybe it's a good idea to note that this is just delta x, the change in x, and this is delta y, the change in y. Okay, however, your z value, okay, in this case, okay, your output, okay, your output delta output is not the same as the output. Okay, so let's go back to our learning activity. So you notice that your change in your change in f is approximately equal 9 times the change in x minus 2 times the change in y plus 8 times the change in z. So is the function most sensitive to changes in x, y, or z? Well, just think of this. If you have something plugging right here, because right here you have a larger coefficient, so that means it will affect your delta f the most. Okay, so let's write down this conclusion. Thus, changes in x have the most effect because it has a larger coefficient. Okay, it has a larger coefficient. Now, let's go back to our lecture note. And now let's take a look at example 3. We want to approximate the change in z as x comma y moves from the point 1 comma 1 to the point 1.01 comma 0.97. Okay, now as you can see right here, you don't really want to find the true value, okay, because I don't want to square 1.01. I don't want to square 0.97, and I definitely don't want to evaluate 4 minus this guy square minus this guy square and then take the square root. I will not do that. Okay, so the best thing I can do right here is to approximate. So that's why we want to use the total differential. So to use the total differential, you will need the partial derivatives. Okay, so right here, notice that your z sub x. Now again, if you want to evaluate this, you can think of this as 4 minus x squared minus y squared to the 1/2 and then apply the power rule, okay? So that's why we have 1 over 2 times the square root of 4 minus x squared minus y squared, and then multiply by negative 2x because of the chain rule. And your z sub y is the same, 1 over 2 times the square root of 4 minus x squared minus y squared times negative 2y because of the chain rule. Now, this is your initial point, and this is your terminal point. So you will need to evaluate your partial derivatives at the initial points, okay? So evaluate partial derivatives at the initial point. Okay, so that means right here my z sub x at 1, 1 should be negative 1 over square root of 2. And your z sub y at 1, 1, well, this is the same thing, negative 1 over square root of 2. And we know that the total differential, the formula, so let's go back to the previous page. We have the partial with respect to x, partial with respect to y, okay, partial with respect to x, partial with respect to y, and then we wanted to multiply by dx and dy. And again, dx is the change in x, and dy is the change in y. So next, we would like to find the change in x and the change in y. So we will do a dx right here and a dy right here. Now to find the change in x or the change in y, you wanted to use terminal minus initial, right? Because if you change from P to Q, sorry, if you move from P to Q, then the change will be Q minus P, right? So terminal for x minus initial for x, and terminal for y minus initial for y. So that should be 0.01 and the negative 0.03, okay? So right here, it's terminal minus initial. Okay, terminal minus initial. So thus, the change in z, okay, the change in z should be approximately equal to dz, the total differential. And the dz right here is partial z over partial x times dx plus partial z over partial y times dy, which is negative 1 over square root of 2 times 0.01 plus negative 1 over square root of 2 times negative 0.03. Okay, now you can try to combine these two because they have the same denominator. So if you combine these two fractions, so that should be a positive 0.03 minus 0.01. So that should be a 0.02. So you can multiply both top and bottom by square root of 2, and you will have 0.01 times square root of 2. Okay, so this will be your answer. Now, by using the calculator, square root of 2 is about 1.4. So you should have a 0.014, yeah. Now the reason I calculate, well, on the test, you don't have to calculate this, okay? So you can stop right here. You can stop right here. The reason I calculate that is because I want you to compare with the true value here. So the exact change is delta z, which is f of 1.01 comma 0.97 minus f of 1 comma 1. So you will really need a calculator, okay? So plugging this value and then minus plugging this value. Okay, so by using the calculator, we have 0.0137. And you can see that our approximation 0.014 is pretty good. Okay, so again, the whole idea for this section, okay, for this lecture note, is to approximate. Okay, you don't really want to find a true value, because sometimes it's impossible without using a calculator. Okay, so the best thing we can do is to approximate. Okay, now we have learned this, and I would like you to do something on your own. So let's take a look at learning activity 17-2-A. Where is my 17-2-A? And let's take a look at number 5. Okay, this is a word problem. So let's read this problem carefully. The reason I want you to practice this problem is because if you take a look at exam 2 from spring 2025 and take a look at multiple choice number 4. Okay, you can see that this is basically the same question. Well, the same question except for the numbers. Okay, you want to use the total differentials to estimate the change in the hypotenuse of a right triangle. Okay, when one leg changes from something to something, and the other leg changes from something to something. Okay, so that's why I want you to practice the learning activity. And after you practice the learning activity, you may come here and try to solve this exam problem. Okay, so the learning activity. We want to estimate the change in the hypotenuse, okay, of a right triangle. So I think it's a good idea to try to draw a picture. It's not necessary, but drawing a picture is always good because you can have some visualization, right? So we have the hypotenuse, let's say Z, and we have two legs, X and Y. So you want to estimate the change in the hypotenuse. The change in the hypotenuse is your delta Z. And if you want to estimate, that will be your dz. Okay, so I want to use the total differential to approximate delta Z. When one leg changes from 6 to 5.95, so you can call this leg your X. So X changes from 6 to 5.95. And the other leg, that should be your Y. Okay, changes from 8 to 8.1. So first, you want to find a function Z, okay, function Z in terms of X and Y. And we know that this is a right triangle. So by Pythagorean theorem, our Z is the square root of X squared plus Y squared. Okay, so that will be the function you are looking for. Okay, Z is a function of X and Y. Okay, so by Pythagorean's theorem, Z equals the square root of X squared plus Y squared. So the total differential right here should be partial Z over partial X times dx plus partial Z over partial Y times dy. So I should have again, you can write this as X squared plus Y squared to the 1/2. Okay, and then you apply the power rule. So I should have X over the square root of X squared plus Y squared times dx plus Y over square root of X squared plus Y squared times dy. Okay, now notice that your dx is the change in X. So terminal minus initial. Okay, terminal minus initial. So that should be a negative 0.05. And your change in Y is your dy. Again, that will be terminal minus initial. So that will be 0.1. Therefore, your change in Z is approximately equal the total differential dz, which is, okay, now we wanted to evaluate this guy right here. So we wanted to plug in the initial value for X, remember? Okay, the initial value for X and Y. So that should be 6 square plus 8 square, which is 36 plus 64, 100. The square root of 100 is 10, so you have 10 in the denominator. And your x value is 6. Okay, so 6 over 10 times negative 0.05 plus, we still have 10 in the denominator, but your y is 8 times 0.1. Okay, 0.1. So right here, I believe, excuse me, I believe we have a 10 in the denominator. Your numerator is negative 0.3 plus 0.8, so 0.5. Okay, 0.5, and that would be 0.05. Okay, 0.05. Therefore, this change is 0.05 centimeters. Now, notice that if you write down the conclusion like this, okay, this is not correct because we don't know the real change. We just know the approximation. So we have to say this change is approximately. Okay, so notice that this is the real change. This is the real change in z, and this is just an approximation. Okay, so the real change in z is approximately equal 0.05 centimeters. Okay, now you know how to do this problem, so you may go to our exam 2 and take a look at number 4, multiple choice question number 4. Okay, try to practice this problem. Okay, you don't know what will be on the test, right? But I think this problem is good to practice. Okay, now let's go back to our lecture note. Let's make a quick summary. So today we learned two major topics, the linear approximation and the total differential. Okay, both topics provide approximations. Okay, so remember in this lecture note, we don't find the true values at all. We want to find an approximation. Okay, the linear approximation is basically the z value on the tangent plane, and we would like to use the z value on the tangent plane, and we would like to use the z value on the tangent plane to be the approximation of the z value on the surface. Okay, and once you know the formula, okay, it's really straightforward. Now the total differential is an approximation of the change. Okay, so notice that the linear approximation is the approximation of a value, okay, of the z value. Now the total differential is the approximation of the change in z. Okay, so if you want to find the approximation of the change, you use total differential. If you want to find an approximation of a specific value, then use linear approximation. Okay, now there are some details in the total differential. Remember, you will need to evaluate your partial derivatives at the initial point. Okay, at the initial point. And for the change in x and the change in y, you will need to use terminal minus initial. Okay, so if you have any questions, please do not hesitate to reach out. Thank you.